The electron configuration of the dinitrogen molecule will be a combination of the two nitrogen atoms sharing electrons in the sigma and pi bonding and anti-bonding orbitals. Since each nitrogen atom has two 2s electrons, the 2 sigma g bonding orbital and the 2 sigma u star anti-bonding orbital will be filled with 2 electrons each. These will cancel out, and as a result the bond order at this point will be 0. Since each nitrogen also has 3 2p electrons, the bonding orbitals get filled first, as they are lower in energy than the corresponding antibonding orbitals. This means that we get one 3 sigma orbital filled and two 1 pi orbitals filled, with none of the antibonding orbitals filled. This gives us the electron configuration 2 sigma g squared, 2 sigma u star squared, 3 sigma g squared, 1 pi u to the power 4, and the bond order as shown in the calculation. Since the bond order is 3, this means that an effective triple bond is shown, which is in accordance with the Lewis structure. The molecular orbital diagram for carbon monoxide is very similar to the diagram for a dinitrogen molecule. This is because the overall number of electrons in each subshell for both molecules is equal. The difference between the molecules and the molecular orbital diagrams is that in the dinitrogen molecule, each atom contributes the same number of electrons, as they are, well, the same atom, both being nitrogen. In carbon monoxide, however, this is not the case, as you have one carbon and one oxygen atom bonded to each other. The oxygen and carbon provide the same number of 1s and 2s electrons, however the oxygen atom provides 4 2p electrons, whereas the carbon provides only 2. This leads to the same molecular electronic configuration as the dinitrogen molecule, with a very similar molecular orbital diagram, and, of course, the same bond order. However, the way they got there is much different. Since the O plus ion and the nitrogen atom have the same electron configuration of 1s2, 2s2, 2p3, or helium 2s2, 2p3, the electron configurations for the O2 2+ and dinitrogen molecules will be the same, and as a result, their molecular orbital diagrams will also be very similar, with 4 bonding orbitals filled and only 1 anti-bonding orbital filled. However, in the molecular orbital diagram for nitrogen, the 1 pi bonding orbitals, which are the 2px and 2py orbitals within the atom, are filled before the 3 sigma bonding orbital, which is the 2pz orbital in the atoms. This is because they are lower in energy. They are lower in energy because the energy gap between the 2s and 2p subshells in nitrogen is low enough that the 2s and 2pz orbitals overlap, as they are both in the same plane. This causes the energy of the 3 sigma, which is the 2pz bonding orbital, to increase above the energy of the two 1 pi orbitals, which are the 2px and 2py orbitals. This is not the case in O2 2+, however, as the oxygen atom itself has a larger energy difference between the 2p and 2s subshells than the nitrogen atom. This means that there is less overlap of the 2s and 2pz orbitals, and the 3 sigma bonding orbital is lower in energy as a result. This is what is expected within most molecules. Overall, this does not affect the bond order though. As stated earlier, there are still 4 bonding orbitals and 1 anti-bonding orbital, so this agrees with the Lewis prediction. As can be seen in the bottom molecular orbital diagram, an O2 molecule has 8 bonding electrons in the bonding orbitals. However, it has 4 antibonding electrons, as each 1 pi g star orbital has 1 electron as well. The O2 2 plus molecular orbital diagram has 8 bonding electrons. However, it has lost the 2 highest energy electrons, which are the ones in the pi antibonding orbitals, and now it only has 2 antibonding electrons in the sigma antibonding orbital, which is shared between the 2 molecules. Since the bond order is calculated through the number of bonding electrons, subtract the number of antibonding electrons, all divided by 2, the O2's bond order is 8 bonding electrons minus 4 antibonding electrons, all divided by 2, which gives a bond order of 2. This suggests a double bond, and this is in agreement with the Lewis representation of an O2 molecule. O2 2+ has 8 bonding electrons as well. However, you only subtract the 2 antibonding electrons present, then divide all of that by 2, which gives a bond order of 3. This suggests a triple bond, which also agrees with the Lewis representation of O2 2+. So, removing 2 electrons from the O2 only increased the bond order because only antibonding electrons were removed, while the number of bonding electrons stayed constant throughout them.